Okay, this is a BC free response question from 2007. It's number 4, which means it's no calculator. And it's again kind of trying to stick with looking at how they might piecemeal out different concepts within one problem and kind of try to award a lot of process point work. This one is giving you f defined for all x greater than 0, where f of e equals 2, so that's a specific spot on the graph. And f prime, the first derivative of f, is given by x squared ln of x. So we've got a derivative expression, and we've got an actual point on the function, and we're told that the function is defined for all positive x values. On this particular one, the first part, finding an equation for a tangent line to the graph, that's just a Calc 1 skill. To do that, they're specifically referencing e comma 2. So we're going to go y minus y1, which is 2, and m times x minus x1, which in this case is e. So I'll just put an e in there. And then what we need to do is figure out, okay, what's the derivative worth, or what's the slope at e? So I'm going to take my derivative at e, and that's going to be e squared times the ln of e, and the ln of e is just 1, so the derivative evaluated at e is e squared. And I'm going to take that value, put it in for m, so we've got y minus 2 equals e squared times x minus e. You certainly can leave it like that. You do not need to do any other adjusting. You've got an equation for the tangent line to the graph at the point e comma 2. And the way the AP is going to award points on this one is they'll give you a point for coming up with the derivative value, and then they'll give you a slope value, and they'll give you a point for the actual expression. And again, you can reorder that expression if you want. You can distribute through, do y equals mx plus b, but that's sufficient. Part B is the graph concave up or concave down on the interval from 1 to 3. So in order to do that, talking about concavity, we need to look at a second derivative. So we need to take f prime, which is x squared ln of x, and we need to take a second derivative. So that's going to involve using a product rule. So we've got 2x times ln of x plus x squared times 1 over x. And let's see, that's going to give us 2x ln of x plus x. And then what we want to do is determine is that graph concave up or concave down on the interval from 1 to 3. And so in looking at this thing, I think there's a couple ways you can do it. I mean, the answer is going to be that it's concave up. So we're going to get a point for correctly giving the answer plus a reason. And then you actually get 2 points just for coming up with the second derivative. So on this one, just generating the second derivative gets you 2 points. And then doing the evaluation that it's concave up because, I should actually write the word because, I should model that, because f double prime is greater than 0 or is positive on the interval 1 to 3. And if you're just looking at this thing and thinking about it, I'm adding, so that's of course positive. 1 to 3, any x value from 1 to 3 is positive. That means this term in the expression is always positive. 2 times numbers between 1 and 3 are always positive. So there's a positive, there's a positive. ln of x from 1 to 3, ln of 1 is 0, so add ln of 1 at 0. But everything else would be a positive value. And we don't need to know what the positive value is, only that it is positive. And then you're going to add it to x. Another way to think about that would be to factor out x. And then you'd have x times 2 ln x plus 1. This expression on the inside is always positive for values from 1 to 3. And this expression on the outside is always positive for values from 1 to 3. So it's another way to think about it. So we have concave up on our function. So f is concave up because the second derivative is greater than 0 or the second derivative is positive on the interval from 1 to 3. So you get 2 points for correctly taking a second derivative, which is a pretty generous set of points in that particular year. And then you get a point for stating that we've got a concave up situation with a reason. And the last one, the reason actually I looked at this one is part C. So it says use anti-differentiation to find f of x. So again, here's our derivative, f prime is x squared ln of x, and we want to find f. So sorry, I'll scroll back and look at it. They're asking us just find f, and they're saying use anti-differentiation. So if I know f prime is x squared ln of x, so that's what, scroll back up here, that's what we're being given. Using anti-differentiation, they're saying take an integral. So take an integral of the left, that gives us f take an integral of the right. That is what makes this a BC problem. There isn't a u substitution that's going to cleanly work here. And so you have to go into that kind of supplementary set of things that we did in order to break an integral apart. This actually ends up being integration by parts. So this is a u dv situation. And actually I dropped off my dx. I should have that in there. So we need to assign a u and a dv. And again, that's a little bit tricky in terms of you just kind of have to get some experience with it and try. And if you feel like you picked the wrong u and the wrong dv, just go and try the other one. So I'm just going to make u equal x squared and then dv equal ln x dx. And then to complete this, then I need a du, and that's going to be 2x dx. And then I need a v, and I find v by integration. So v on this thing is going to be 1 over x. So then my expression is so u dv is this thing, and then I've got that is equal to u times v, so x squared times 1 over x, minus, and then I've got v du. So let's see, v du. So v, that's 1 over x, and du is 2x dx. So that's going to be x minus, let's see, this would be 2 dx, this thing, and then I've got x minus 2x plus c, which is going to give me negative x plus c. So this thing is looking like I went off the rails somewhere if I'm looking at what I just did. And let's just see if I can track through where my error came. Because we're definitely undoing a product rule, two things being multiplied together. So we're going to use a u dv. So I made my u equal x squared. I took the correct du. I made my dv equal ln of x, and that's my mistake. When you integrate ln, you don't get 1 over x. When you integrate 1 over x, you get ln of x. So actually what I did here was incorrect. This is a common error that students make. And it just, I don't know, something about this answer just feels like I was going on the wrong path, and sure enough I was. You cannot cleanly integrate ln of x. There are other tools we developed to integrate it. Actually, coincidentally, I use integration by parts as a way to knock it apart. I don't think this is a nested integration by parts problem, though. So what this is telling me is perhaps I can go through here and maybe make a different assignment. So I could say u equals ln of x, and then let's make dv the x squared dx. So let's try that way and see if that gets me something that I can do a little cleaner. And again, the reason this is wrong, or what fell apart here, is this is not correct in terms of the integration that I was doing. So let's try it this way. So let's see, we've got our u and our dv. That's just assigning it the other direction. And then we've got du is, well, let's see, what would the derivative of ln of x be? There's my 1 over x. So that is the derivative of the ln of x. So if I take that derivative, then I get 1 over x times dx. And then when I integrate this thing, I'm going to get v equals x cubed over 3. So now let's see, that would be uv, so it would be x cubed over 3 times the ln of x minus v du. So that would be, when I multiply these two together, I would get integral of v du. So that's going to be x squared over 3 dx. That actually is something you can integrate. I can add a power, divide by the power. So let's see, I'm going to keep this one the same. Then I'm going to add a power, divide by that power. So I'm going to have x cubed over 9, and I've got to remember my plus c. It definitely, the steps are clean. This looks a lot better in terms of how we would tackle it. And so often that happens where you choose a wrong path and you make a mistake. And I certainly could have edited that out and presented a different video, but I think it's important to see mistakes because you're likely to make them as well as you're working. And just to recognize when something feels a little bit off, perhaps look back at places where common mistakes get made. And that definitely was one very, very common error that I made. So doing this correctly, getting through to the antiderivative, on this one gets us to a plus c. And now what we need to do is actually take and solve for it. So we're going to put in the e comma 2 to solve for this. So again, what we've just found is f of x. It's an expression for f of x. And then we need to plug in e comma 2. So I'm going to plug in e comma 2. And let's see, e comma 2 is going to go in. So 2 goes in for y. And e goes in here. So I've got e cubed over 3 ln of e minus e cubed over 9 plus c. And let's see what we would get. Ln of e is just 1, so that's e cubed over 3 minus e cubed over 9 plus c. I can combine those two fractions, so this is 3e cubed over 9 minus 1e cubed over 9, so that's 2e cubed over 9 plus c. So then c is 2 minus 2e cubed over 9. So there's solving for c. And then I'm going to take that thing that I just solved, and I'm going to pop it back into the expression. So I've got x cubed over 3 ln x minus, let's see, it'd be x cubed over 9, and then it would be plus 2 minus 2e cubed over 9. And that 4-term expression ends up being our answer on this one. So that is our result. That only gets us a point, the final answer. Solving for c, so showing that intermediate step gets us a point, and then correctly doing the antiderivative. This set of the u dv here of, I guess that would be kind of this set of steps. That generates 2 points. So the whole thing's worth 4. And again, the common mistakes are going to happen. And in real time, you may make a mistake, realize it's going off the rails. And when you're actually taking the AP exam, you won't have the time to pause and redo it. You just need to recognize that it's something isn't feeling right, and go back and look at the places where mistakes can happen. And certainly on integration by parts, making an assignment error is really frequent. And then me making kind of the just slipping up and doing the derivative instead of the integral when I was looking at doing the dv and moving it to the v. I think is a really common and easy place to make a mistake as you're moving through a problem. So that, again, we'll scroll up on this one. That is a 3-part problem where they're asking 3 very distinct skills using the same problem. And it's a good way in which I think they're going to kind of go about things this year, trying to use one kind of base problem and then asking a bunch of different branches of the class from that problem. So hopefully a good one to practice headed into the AP exam.